In mathematics, a partial differential equation is a differential equation that contains unknown multivariable functions and their partial derivatives, which deal with functions of a single variable and their derivatives. PDEs are used to formulate problems involving functions of several variables, and are either solved by hand, or used to create a relevant computer model. PDEs can be used to describe a wide variety of phenomena such as sound, heat, electrostatics, electrodynamics, fluid flow, elasticity, or quantum mechanics. These seemingly distinct physical phenomena can be formalized similarly in terms of PDEs. Just as ordinary differential equations often model one-dimensional dynamical systems, partial differential equations often model multidimensional systems. PDEs find their generalization in stochastic partial differential equations. Introduction. Partial differential equations are equations that involve rates of change with respect to continuous variables. The position of a rigid body is specified by 6 numbers, but the configuration of a fluid is given by the continuous distribution of several parameters, such as the temperature, pressure, and so forth. The dynamics for the rigid body take place in a finite-dimensional configuration space. The dynamics for the fluid occur in an infinite-dimensional configuration space. This distinction usually makes PDEs much harder to solve than ordinary differential equations. But here again there will be simple solutions for linear problems. Classic domains where PDEs are used include acoustics, fluid flow, electrodynamics, and heat transfer. A partial differential equation for the function is an equation of the form if f is a linear function of u and its derivatives, then the PDE is called linear. Common examples of linear PDEs include the heat equation, the wave equation, Laplace's equation, Helmholtz equation, Klein-Bordern equation, and Poisson's equation. A relatively simple PDE as this relation implies that the function u is independent of x. However, the equation gives no information on the function's dependence on the variable y. Hence the general solution of this equation is where f is an arbitrary function of y. The analogous ordinary differential equation is which has the solution where c is any constant value. These two examples illustrate that general solutions of ordinary differential equations involve arbitrary constants, but solutions of PDEs involve arbitrary functions. A solution of a PDE is generally not unique. Additional conditions must generally be specified on the boundary of the region where the solution is defined. For instance, in the simple example above, the function f can be determined if u is specified on the line x equals 0. Existence and uniqueness. Although the issue of existence and uniqueness of solutions of ordinary differential equations has a very satisfactory answer with the Picard-Lindelof theorem, that is far from the case for partial differential equations. The Cauchy-Kowalewski theorem states that the Cauchy problem for any partial differential equation whose coefficients are analytic in the unknown function and its derivatives has a locally unique analytic solution. Although this result might appear to settle the existence and uniqueness of solutions, there are examples of linear partial differential equations whose coefficients have derivatives of all orders but which have no solutions at all. See Louis. Even if the solution of a partial differential equation exists and is unique, it may nevertheless have undesirable properties. The mathematical study of these questions is usually in the more powerful context of weak solutions. An example of pathological behavior is the sequence of Cauchy problems for the Laplace equation with boundary conditions where n is an integer. The derivative of u with respect to y approaches 0 uniformly in x as n increases. But the solution is this solution approaches infinity if nx is not an integer multiple of pi for any non-zero value of y. The Cauchy problem for the Laplace equation is called ill-posed or not well-posed, since the solution does not depend continuously upon the data of the problem. Such ill-posed problems are not usually satisfactory for physical applications. Notation. In PDEs, it is common to denote partial derivatives using subscripts. That is, especially in physics, del or nabla is often used to denote spatial derivatives, and for time derivatives. For example, the wave equation can be written as or where delta is the Laplace operator. Examples: heat equation in one space dimension, the equation for conduction of heat in one dimension for a homogeneous body has where U is temperature, and alpha is a positive constant that describes the rate of diffusion. The Cauchy problem for this equation consists in specifying U equals F, where F is an arbitrary function. General solutions of the heat equation can be found by the method of separation of variables. Some examples appear in the heat equation article. They are examples of Fourier series for periodic f and Fourier transforms for non-periodic f. Using the Fourier transform, a general solution of the heat equation has the form where f is an arbitrary function. To satisfy the initial condition, f is given by the Fourier transform of f, that is if f represents a very small but intense source of heat. Then the preceding integral can be approximated by the delta distribution, multiplied by the strength of the source. For a source whose strength is normalized to 1, the result is and the resulting solution of the heat equation is this is a Gaussian integral. It may be evaluated to obtain this result corresponds to the normal probability density for x with mean 0 and variance 2 alpha t. The heat equation and similar diffusion equations are useful tools to study random phenomena. Wave equation in one spatial dimension. The wave equation is an equation for an unknown function u of the form here you might describe the displacement of a stretched string from equilibrium, or the difference in air pressure in a tube, or the magnitude of an electromagnetic field in a tube. And m is a number that corresponds to the velocity of the wave. The Cauchy problem for this equation consists in prescribing the initial displacement and velocity of a string or other medium, where f and g are arbitrary given functions. The solution of this problem is given by D'Alembert's formula. This formula implies that the solution depends only upon the data on the segment of the initial line that is cut out by the characteristic curves that are drawn backwards from that point. These curves correspond to signals that propagate with velocity m forward and backward. Conversely, the influence of the data at any given point on the initial line propagates with the finite velocity m. There is no effect outside a triangle through that point whose sides are characteristic curves. This behavior is very different from the solution for the heat equation, where the effect of a point source appears instantaneously at every point in space. The solution given above is also valid if chi less than 0, and the explicit formula shows that the solution depends smoothly upon the data. Both the forward and backward Cauchy problems for the wave equation are well posed. Generalized heat-like equation in one space dimension, where heat-like equation means equations of the form, whereas a Sturm-Liouville operator subject to the boundary conditions. Then, if where spherical waves are waves whose amplitude depends only upon the radial distance r from a central point source. For such waves, the three-dimensional wave equation takes the form this is equivalent to, and hence the quantity ρ satisfies the one-dimensional wave equation. Therefore a general solution for spherical waves has the form where f and g are completely arbitrary functions. Radiation from an antenna corresponds to the case where g is identically 0. Thus the waveform transmitted from an antenna has no distortion in time. The only distorting factor is 1 r. This feature of undistorted propagation of waves is not present if there are two spatial dimensions. Laplace equation in two dimensions. The Laplace equation for an unknown function of two variables phi has the form solutions of Laplace's equation r, called harmonic functions. Connection with holomorphic functions. Solutions of the Laplace equation in two dimensions are intimately connected with analytic functions of a complex variable. The real and imaginary parts of any analytic function are conjugate harmonic functions. They both satisfy the Laplace equation, and their gradients are orthogonal. If f equals u plus I, then the Cauchy-Riemann equations state that, and it follows that conversely, given any harmonic function in two dimensions, it is the real part of an analytic function, at least locally. Details are given in Laplace equation. A typical boundary value problem. A typical problem for Laplace's equation is to find a solution that satisfies arbitrary values on the boundary of a domain. For example, we may seek a harmonic function that takes on the values u on a circle of radius 1. The solution was given by Poisson. Petrovsky shows how this formula can be obtained by summing a Fourier series for phi. If r less than 1, the derivatives of phi may be computed by differentiating under the integral sign, and one can verify that phi is analytic, even if u is continuous but not necessarily differentiable. This behavior is typical for solutions of elliptic partial differential equations. The solutions may be much more smooth than the boundary data. This is in contrast to solutions of the wave equation, and more general hyperbolic partial differential equations, which typically have no more derivatives than the data. Euler-Trichummer equation. The Euler-Trichummer equation is used in the investigation of transonic flow. Advection equation. The advection equation describes the transport of a conserved scalar psi in a velocity field u equals. It is. If the velocity field is solenoidal, then the equation may be simplified to in the one-dimensional case where u is not constant and is equal to psi. The equation is referred to as Berger's equation. Ginsburg-Landau equation. The Ginsburg-Landau equation is used in modeling superconductivity. It is where p, q, c and gamma are constants and I is the imaginary unit. The dym equation. The dym equation is named for Harry dym and occurs in the study of solitons. It is initial boundary value problems. Many problems of mathematical physics are formulated as initial boundary value problems. Vibrating string. If the string is stretched between 2 points where x equals 0 and x equals L and u denotes the amplitude of the displacement of the string, then u satisfies the one-dimensional wave equation in the region where 0 less than x less than L and t is unlimited. Since the string is tied down at the ends, u must also satisfy the boundary conditions as well as the initial conditions. The method of separation of variables for the wave equation leads to solutions of the form where the constant k must be determined. The boundary conditions then imply that x is a multiple of sin kx, and k must have the form where n is an integer. Each term in the sum corresponds to a mode of vibration of the string. The mode with n equals 1 is called the fundamental mode, and the frequencies of the other modes are all multiples of this frequency. They form the overtone series of the string, and they are the basis for musical acoustics. The initial conditions may then be satisfied by representing f and g as infinite sums of these modes. Wind instruments typically correspond to vibrations of an air column with one end open and one end closed. The corresponding boundary conditions of the method of separation of variables can also be applied in this case, and it leads to a series of odd overtones. The general problem of this type is solved in Sturm-Liouville theory. Vibrating membrane. If a membrane is stretched over a curve C that forms the boundary of a domain D in the plane, its vibrations are governed by the wave equation if D greater than 0 and is in D. The boundary condition is U equals 0 if is on C. The method of separation of variables leads to the form which in turn must satisfy the latter equation is called the Helmholtz equation. The constant k must be determined to allow a non-trivial v to satisfy the boundary condition on C. Such values of k2 are called the eigenvalues of the Laplacian in D, and the associated solutions are the eigenfunctions of the Laplacian in D. The Sturm-Liouville theory may be extended to this elliptic eigenvalue problem. Other examples. The Schrödinger equation is a PDE at the heart of non-relativistic quantum mechanics. In the WKB approximation it is the The above equations are linear in the sense that they can be written in the form O equals F for a given linear operator A and a given function f. Other important nonlinear equations include the Navier-Stokes equations describing the flow of fluids, and Einstein's field equations of general relativity. Also see the list of nonlinear partial differential equations. Classification. Some linear, second-order partial differential equations can be classified as parabolic, hyperbolic and elliptic. Others, such as the Euler-Tricamer equation, have different types in different regions. The classification provides a guide to appropriate initial and boundary conditions, and to smoothness of the solutions. Equations of first-order linear equations of second-order assuming the general second-order PDE in two independent variables has the form where the coefficients a, b, c etc. may depend upon x and y. If over a region of the xy plane, the PDE is second-order in that region. This form is analogous to the equation for a conic section. More precisely, replacing x by x, and likewise for other variables, converts a constant coefficient Pd into a polynomial of the same degree, with the top degree being most significant for the classification. Just as one classifies conic sections and quadratic forms into parabolic, hyperbolic, and elliptic based on the discriminant, the same can be done for a second-order PDE at a given point. However, the discriminant in a PDE is given by due to the convention of the xy term being 2b rather than b. Formally, the discriminant is with the factor of 4 dropped for simplicity. For example, solutions of Laplace's equation are analytic within the domain where they are defined, but solutions may assume boundary values that are not smooth. The motion of a fluid at subsonic speeds can be approximated with elliptic PDEs, and the Euler-Tricamer equation is elliptic where x less than 0. Equations that are parabolic at every point can be transformed into a form analogous to the heat equation by a change of independent variables. Solutions smooth out as the transformed time variable increases. The Euler-Tricamer equation has parabolic type on the line where x equals 0. Hyperbolic equations retain any discontinuities of functions or derivatives in the initial data. An example is the wave equation. The motion of a fluid at supersonic speeds can be approximated with hyperbolic PDEs, and the Euler-Tricamer equation is hyperbolic where x greater than 0. If there are n independent variables x1, x2, xn, a general linear partial differential equation of second order has the form. The classification depends upon the signature of the eigenvalues of the coefficient matrix I, J. Elliptic. The eigenvalues are all positive or all negative. Parabolic. The eigenvalues are all positive or all negative, save one that is 0. Hyperbolic. There is only one negative eigenvalue and all the rest are positive, or there is only one positive eigenvalue and all the rest are negative. Ultra-hyperbolic. There is more than one positive eigenvalue and more than one negative eigenvalue, and there are no zero eigenvalues. There is only limited theory for ultra-hyperbolic equations. Systems of first-order equations and characteristic surfaces. The classification of partial differential equations can be extended to systems of first-order equations, where the unknown u is now a vector with m components, and the coefficient matrices A nu are m by m matrices for nu equals 1. The partial differential equation takes the form where the coefficient matrices A nu and the vector B may depend upon x and u. If a hypersurface S is given in the implicit form where phi has a non-zero gradient, then S is a characteristic surface for the operator L at a given point if the characteristic form vanishes. The geometric interpretation of this condition is as follows. If data for U are prescribed on the surface S, then it may be possible to determine the normal derivative of U on S from the differential equation. If the data on S and the differential equation determine the normal derivative of U on S, then S is non-characteristic. If the data on S and the differential equation do not determine the normal derivative of U on S, then the surface is characteristic, and the differential equation restricts the data on S. The differential equation is internal to S. A first-order system LU equals 0 is elliptic if no surface is characteristic for L. The values of U on S and the differential equation always determine the normal derivative of U on S. A first-order system is hyperbolic at a point if there is a space-like surface S with normal shear at that point. This means that, given any non-trivial vector eta orthogonal to xi, and a scalar multiplier lambda, the equation has m real roots lambda 1, lambda 2, lambda m. The system is strictly hyperbolic if these roots are always distinct. The geometrical interpretation of this condition is as follows. The characteristic form QE equals 0 defines a cone with homogeneous coordinates zeta. In the hyperbolic case, this cone has m sheets, and the axis zeta equals lambda xi runs inside these sheets. It does not intersect any of them, but when displaced from the origin by eta, this axis intersects every sheet. In the elliptic case, the normal cone has no real sheets. Equations of mixed type. If a PDE has coefficients that are not constant, it is possible that it will not belong to any of these categories but rather be of mixed type. A simple but important example is the Euler-Tricamer equation, which is called elliptic hyperbolic because it is elliptic in the region x less than 0, hyperbolic in the region x greater than 0, and degenerate parabolic on the line x equals 0. Infinite order PDEs in quantum mechanics. In the phase space formulation of quantum mechanics, one may consider the quantum Hamilton's equations for trajectories of quantum particles. These equations are infinite order PDEs. However, in the semi-classical expansion, one has a finite system of odes at any fixed order of h. The evolution equation of the Wiener function is also an infinite order PDE. The quantum trajectories are quantum characteristics, with the use of which one could calculate the evolution of the Wiener function.